All right, good afternoon, everyone. I'm Michael Manser. I'm the director for the Center for Transportation Safety. I want to welcome you to our presentation series. This is the Innovative Projects to Improve Transportation Safety in Texas. And I'll give you a really quick background. So the Center for Transportation Safety is provided with funding from the state of Texas each year. And with that funding, we provide money to a series of PIs to do innovative projects on some topic, usually of their choosing, that addresses transportation safety in Texas. And what we've been asking staff to do lately is to report out on what they've done and all the great things that their project has accomplished. And that's really the basis of this presentation series, is to disseminate that information from these projects out to everybody. I see that we have like 33 people online, which is absolutely awesome. Thank you for joining us today. We have a couple external people who have joined us, and that is we're dipping our toe into opening up this presentation series to people outside of TTI. This is only our second presentation, and it looks like certainly on the third one, we'll open it up to, for example, all the TSSs and TxDOT and other stakeholders in Texas. And I want to thank, I do notice we have at least one TxDOT staff who's joined us today, and I want to thank you, Elizabeth, for joining us. Okay, so without delaying this any further and get you guys onto the really interesting stuff, I want to introduce to you Minh and Mike Pratt. They have done a project. The title is Using Advanced Techniques to Data Mine Pedestrian Crash Data. The title's kind of a mouthful. And they've done some really, really interesting work here. The thing I like, and they will probably touch on this in their presentation, is that a lot of the methods that they've developed here to look into pedestrian issues can be used to look into other issues like motorcyclists, other crash information in the crash reports, etc. So it has a lot of, the work that they've done has a lot of versatility in a lot of different ways. So with that, I'm going to turn it over to Minh and Mike and let y'all take it from here.
Okay, great. Thank you, Mike. Can everybody hear me okay?
Yep, we can hear you.
Great. So I'm Minh. I'm a research engineer in the Dallas office of TTI, the Research and Implementation Division. Mike Pratt will be joining me, and we're going to tag team on this presentation. So I'll just go ahead and just get started. So some of you may have seen a sort of a preview of this presentation. We actually presented our preliminary findings last summer in San Antonio at the statewide Pedestrian Coalition meeting there, and at that forum. And then we kind of wrapped up the study shortly thereafter and wrapped up the final report last November. So this is a presentation of our final findings. Let me see. And also we'd like to thank Michael and also Robert Wunderlich for helping us to fund this project. It was a very neat project that allowed us to explore a lot of really neat stuff. So a little bit of background. Most of you may be aware already that pedestrian fatalities have been increasing over the years, last decade or so. And that's certainly true nationally, as you can see here in the graph, in terms of showing not only the absolute numbers of the pedestrian fatalities, but also the percentage and its trend over the last decade or so. In Texas, that is also true, as you can see here in this graph.
We are also we have had now two leadership seminars that we've called them, so an annual event around the November.
Okay, I'll continue. As you can see here in this chart, it shows the pedestrian, the fatal crashes, and then the fatal pedestrian crashes, and the percentage shown in that the gray line. And that also has increased over the years. And you can see now it's hovering right at about 22%, which is about a fifth or 1 out of 5 pedestrian-related crashes result in fatal. And that probably isn't a surprise to most of you. one of the biggest problems that a lot of us face in terms of looking at crash data, particularly for vulnerable roadway users, such as pedestrian crashes, is the lack of detail in the structured part of the CRIS data. So there's a lot of really good information about the motorists and the the vehicle in terms of what was happening at the time of the crash. But what's lacking is a lot of the details for the pedestrian themselves or the vulnerable roadway user. And that's really critical, as you know, to identify, to be able to match up an appropriate countermeasure. So a lot of that information is normally found in the crash narratives of the CR3 report, as well as the diagram, which is an example shown there on the right. So what this problem, or what this project was about, was to really see if we can use artificial intelligence, AI, different techniques of that, to see if we can data mine those two parts of the crash report that traditionally just hasn't been, the information in there hasn't been extracted in a very efficient way. A lot of us have done manual reviews of those, and we know that it takes time and effort to infer that information. But if we can do it in a much more efficient way by using some AI techniques to do that, that's what really was the crux of this this project here. So we were going to develop we developed a crash database, starting with the pedestrian crashes and hoping to expand that, as Mike kind of alluded to. The concepts that we applied here really is applicable to any type of other crashes. Bicyclists, motorcyclists, for example. Those are the other things that certainly could be adapted so that it could do the same things for those types of crashes. So it was really to supplement the structured part of the data with some of the unstructured part in terms of crash typing. I'll get into that in a little bit. And then the pedestrian intentionality, or what we're calling the pedestrian intentionality. We're also, this was a great opportunity for us to collaborate with another agency, the Southern Regional Climate Center, and where we were able to, or their data scientists were able to help us to integrate some of the weather data that is not present in the CRIS data, and then also some sun glare data that I'll get into in another slide. So first, the pedestrian or the crash typing process. Some of you may be familiar with Federal Highway's PBCAT tool, the Pedestrian and Bicycle Crash Analysis tool. Version 3, I think, was available a couple years ago now. It basically boils down the pedestrian or the vulnerable roadway user, the bicyclist or the pedestrian. It boils down their maneuvers as well as the motorist maneuver into these 81 different classes shown here in this matrix. So for example, if the vehicle is going straight and then the pedestrian is crossing from the right, it would be designated as an S-CR. And so this kind of information was the thing that we kind of needed in order to, again, determine the appropriate countermeasure for those locations. And to do it at a very large scale was very time consuming and required a lot of effort. So one of the things that we were trying to do was to see if we can apply these different techniques in order to really mine that data really from the crash narrative portion of it. So this was our process in terms of mining the crash narratives. We were looking at really two methods, or we were looking at two specific things at first. The binary, which is we were trying to define the intentionality of the pedestrian, whether or not they were intended or unintended, meaning that was the pedestrian there intending to be a pedestrian crossing the roadway and whatnot. And I'll get into that in the next slide. As well as the multi-classification, where the pedestrian maneuvers is really what we were after. Again, going back to that matrix that I had on the previous slide, what was their maneuver? Were they trying to cross the roadway, or were they trying to walk along the roadway parallel to traffic or against traffic? Those were the kinds of things that we were looking for there. We employed natural language processing. Some of you may already be using this right now. It's using large language models. It's just a subset of AI, but it's using large language models to be able to really kind of infer what it is that you need from whatever information that you're trying, the data that you're trying to extract information from. The couple of the large language models that we really employed for this is called BERT and Roberta. Those are the two main ones, but we explored a lot of other types in our full documentation, full report. You'll see all the different types that we tested. In terms of pedestrian intentionality, most of us really, when we think of a pedestrian crash, we're thinking of sort of the examples on the left side where people are crossing the roadway or walking along the roadway and then getting hit. Those are what we classified as intended for the purposes of our study. On the right side are what we call unintended, although they fit the definition, the current definition of a pedestrian, meaning that if a person was inside their vehicle and stopped alongside the roadway and got out and then got hit or struck as while they were on foot, they were also getting coded as a pedestrian. But for our purposes, the countermeasures that would be employed there are very different than what we traditionally would think of in terms of pedestrian crashes. So for our purposes, we weren't including those types of unintended pedestrian crashes. Also, we saw a lot of, a number of e-scooter related crashes also in the data that showed up in the pedestrian data set that we had, as well as emergency responders when they are on the scene working a crash or some kind of incident, and then also if they're struck, they get coded as pedestrian. And so they really weren't out there for the intention of walking along the roadway. So we did not consider them as pedestrians in this case, as intended pedestrians. So when we did the NLP, or the natural language processing, and applied our models to the data set, one of the things that we did was we developed first a training data set in order to train our models. Did this for both the binary and for the multi-class approach. And then we started looking at the results in terms of the accuracy and another metric called the F1 measure in terms of measuring how accurate it is in terms of false positives, et cetera. And what we found was it actually, through several iterations, it actually resulted in very good high accuracy and very high F1 measures. And so we felt very confident about that and felt comfortable applying that actually to the full data set, and that's what we did here. When we did that, we also kind of classified our crashes between ones that are on freeways or controlled access facilities versus non-controlled access facilities, and looked at the differences in terms of the patterns. But what we found overall when we applied our models to the full data set, which we had 3 years worth of data in 3 major cities, so that's over 4,400 crashes in our data set that we applied this to. What we found was about 70-30 split between intended pedestrians based on our definition and unintended pedestrians. But what was really interesting was when you dug into it in terms of the ones that are on freeways or controlled access facilities, it was about a 50-50 split. And that actually closely correlated with some of the previous stuff that we've done where we've investigated it at a very high level. And also from what we were hearing from some of the districts in terms of their monthly fatal crash reviews that they would do, a lot of them would be on freeways, and it was as a result of people getting out of their vehicles and then getting hit, or unintended, in other words. So we thought that that was an interesting find. But on the non-controlled access facilities, it more closely mimicked the overall, which is what you would expect, because on the arterials and whatnot, that's where you would expect to see pedestrians. So we thought that this was a really good find, and it kind of led to the question of whether or not we're overcounting pedestrian crashes, or maybe what we should think about is perhaps the pedestrian definition. Perhaps there should be a subclass of the pedestrians. In other words, some of those that we're not that weren't intended to be there as pedestrians, perhaps they just needed to be counted in a different way. On the other classification that we did, which is the multi-class, again, using that training data set, we basically grouped all of the pedestrian maneuvers to a simplified classification system. The reason why we needed to do that was because, as you saw, that matrix was pretty large, had 81 different classes overall. I believe there's about, I don't know, at least a dozen, if not more, in terms of the columns. And so there was a lot of imbalance when we were looking at that. And because of that imbalance, it was very hard to model. So we had to start simplifying it a little bit in order to get better results. And so you can see here just a couple of the results in terms of our iterations. When we did it with 8 classes, we had pretty low accuracy and a pretty low F1 measure. Then we cut that in half to 4 classes and definitely improved the accuracy and the F1 measure. And then we reduced it again down to 2 classes. And then we saw that the accuracy and the F1 measure was definitely more acceptable in terms of what we would use for modeling purposes. But even with that, it didn't lead to our end goal, which is, being able to classify those maneuvers down to the point where we could at least say it was more than just crossing versus non-crossing, which is what we ended up with in the 2 class, but also to see if we can differentiate between the ones that were crossing either from the right or from the left, or if they weren't crossing it, were they stationary or were they walking along the roadway in parallel to with the direction of traffic or in the opposite direction and whatnot. So that's where we started exploring other techniques, and we used computer vision as well as machine learning in terms of the SVM, the support vector machine models, to apply that to the crash diagrams. And then what we did was we basically determined, based on our test data set, what we thought was an acceptable probability threshold at 90%. I'll get into that later, where we, anything that was at least 90% or higher, we had fairly good confidence that we could apply and then try to subclassify those crashes a little bit more. So this chart here on the right kind of shows the results of our test, where we had, again, just on the training data set, we had 600 of them were in the crossing, but we had, about 218 of those were classified with a probability of 90% or more. So with each iteration, it would actually give you a kind of a probability in terms of how it thinks it actually predicted in terms of the models. And so what we see there was in our crossing and non-crossing the same. If we just applied this align just across that 90%, we felt that if we used the results that was a probability of 90% or higher, then those would be good for us to try to subclassify, because those are the ones that we have confidence in the results. So that's what we did. Again, using computer vision, this is just a flow chart of how we did it, how we approached it. First, you got to label the data. For those of you that have worked with this kind of stuff before, you know that in order to develop your training data set, you have to annotate it. So we were using a third-party software to do that, where we developed we took the diagrams, and there was a lot of variability, as you can imagine, in the diagrams. I don't know how familiar some of you are to the diagrams, but they used to be hand-drawn, but thankfully most of them are not hand-drawn anymore. My understanding is a lot of the officers use some kind of program where they drag and drop icons. And so that's helped a lot. But even with that, there's really no set way of doing it. So we had a lot of different variability. There was a lot of diagrams that we just we couldn't use it at all. But the ones that we could use, we went ahead and we labeled those. Then we ran it through a product called YOLO, which some of you may be familiar with and are using. We're using that in terms of just detecting the different objects in our diagram. These are static, obviously. And then we ran the output from that to the SVM models, or the machine learning part of it, in terms of predicting what the maneuver was for the pedestrian. And so this table here kind of shows you the results, particularly the ones that we were focused on were the ones where it had a probability of 0.9 or higher, where we were able to classify or subclassify not just the crossing and non-crossing, but we were able to subclassify them into whether they were crossing from the left or crossing from the right or from an unknown direction, which is what the CU is, for example. And this is based on what we were able to infer from the diagrams that we had a high probability of for the based on the binary, or I'm sorry, the crossing versus non-crossing model from the narratives. And so you can see here that the results are better, but they're still not quite there up to par. And what really was the key takeaway for us was that this framework basically demonstrated that it's possible, it has potential. With some refinement, we think that it can be much higher in terms of accuracy. And then with that, I'm going to turn it over to my colleague, Mike Pratt, to go over the weather data and then also some of the predictions where we applied all of the stuff that we learned to the data set. So Mike, are you there?
Yes, thank you, Minh.
Sure.
Okay, so yeah, starting with the discussion of the weather data here, as Minh mentioned earlier, it's always on our wish list item that we would like to know more about these crashes, what exactly happened, how can we tease out more details, and what are perhaps some other data sources that we could bring in so we can get a better understanding of what's going on with these crashes. So we'll talk some about the weather data here. So we worked with our colleagues over at the Southern Regional Climate Center. We developed an API to add some weather and climate details. We looked at things like temperature and visibility, several variables that dealt with precipitation, cloud cover, and especially we looked at sun glare. There's been some discussion in the literature about sun glare and what role it might play, especially with pedestrian vehicle crashes. Are some of these crashes happening because drivers are not seeing the pedestrians because the sun is in their eyes? Okay, the next slide, please. Right, so just to give you an idea of the spatial coverage for the weather data, we used weather stations, which are typically located at airports, and we're showing you here maps of the 3 different cities that we had in this effort: Dallas, Austin, and San Antonio. There were 8 weather stations in Dallas and 4 each in Austin and San Antonio. And then the plotted dots here are the locations of the pedestrian vehicle crashes in the 3 cities. So we had some pretty good coverage as far as the crash locations, and we worked with the weather stations, interpolating where necessary to get an idea of the weather conditions at the crash location when the crash happened. And next slide, please. Right, so digging into the details some here, one of the issues of interest was sun glare, and we approached from 2 different angles to try and determine whether sun glare was a contributing factor in the crashes that we examined. First, we looked at the CRIS database, either by parsing out the key words in the narratives. We had a tool that could do that for us. Or there's also an other factor variable in the actual CRIS database, and it has one code for sun or headlight glare. So we looked for evidence in CRIS, either the other factor variable or in the narratives, for whether or not sun glare was an issue. We found 65 crashes out of the 4,442 in our database that had some evidence of sun glare being an issue in the CRIS database. We also brought in the weather data. We had information about things like, obviously, the time of the crash, and then we were able to determine where the sun was in the sky. Was it low enough in the sky that glare might have been an issue? For that, we needed to know the time, the sun position, and also the direction of travel for the vehicle. Was the driver driving into the sun or away from it? With that second analysis, we identified 565 crashes that were flagged as possibly sun glare related, yet did not have any evidence for sun glare in the CRIS database. A total of 616 crashes occurred during conditions when sun glare may have been an issue. There may be some double counting because a crash could have been flagged as glare related based on the weather data, and also in CRIS, there were 630 total crashes that were counted in both categories. The key question here is, why the difference? Why were there some crashes that had some evidence of sun glare in the CRIS database, but didn't occur during the weather conditions when sun glare may have been a factor, or vice versa? Why would there be some crashes during conditions where sun glare might have, the conditions might have led to sun glare, but it wasn't documented in CRIS? Well, there could be several reasons. Some of these crashes may have been glare related, but the glare just did not get identified or documented during the crash investigation process. It might not have come up in the interviews, or might not have been documented. And it's also possible that some crashes may not have been affected by sun glare, even though they occurred in times of day and in conditions when sun glare could have been an issue. So to me, really, the key takeaway with this investigation was to determine if a certain specific issue like sun glare was an issue. It's necessary to investigate from multiple angles, looking at multiple data sources. Next slide, please. All right, so here's a graph that shows the crash distribution by hour. So first, the blue data series is the crashes that were flagged as glare related, and there's no surprise here. We see more of them during the periods when the sun is lower in the sky. The gray data series is the total crashes by hour, and no surprise here either. There's very few pedestrians during the very early hours of the day, like 3, 4, or 5 a.m. We see definitely more pedestrian vehicle crashes once we start getting into the morning, and especially in the evening periods when you might have a mix of commuters and also tourists or people coming downtown for dinner, things like that. So an intuitive trend here, just looking at the hours for the crashes. Next slide, please. All right, so the next challenge was to see if we can predict crash severity. And for this, we looked at just the intended pedestrians. So this is people who were actually walking and intending to be pedestrians, as opposed to just people who had to get out of their cars because they broke down or whatever. And we split it into two groups: pedestrians on controlled access facilities. There were relatively few crashes in this bin, just 66 of them. And our goal here was to see if we can determine what were the factors that led to a crash being of fatal severity, so K on the Cabco scale. More crashes in the non-controlled access category. So these are pedestrians on the non-controlled access facilities, city streets, for instance, 637 such crashes. And here we wanted to look at what would predict the severity being fatal or incapacitating injury, so K or A. You can see in the frequency table here, no surprise, most of the pedestrian vehicle crashes that happen on a controlled access facility would be high severity, either K or A. A somewhat more even distribution of the severities for the crashes on the non-controlled access facilities, very few property damage only, but otherwise a good distribution among K, A, B, and C. So some factors we might consider are speeds, looking at speed limit, geometry, and traffic volume, and then also the crash types. Minh showed you earlier the matrix of the different crash types, and then sun glare and maybe some demographic variables. So let's see what we could find with our data here. This is the functional form, a complicated equation, but basically it's predicting the probability of high severity for a crash, given that a crash has occurred. So it's a logit model or a log odds model, and we have a vector of the predictor variables, and the challenge here would be, okay, which variables are statistically significant, and what are the trends, and what can we learn from them? Okay, next slide, please. All right, so first let's look at the controlled access facilities. So probability of a fatality occurring. There were 66 crashes here, so as always with modeling, it's more likely to find interesting trends when you have a higher sample size, and somewhat limited sample size here. And shout out, by the way, goes to Srinivas Jitapalli, who was on our team for this project as well, and he was the one who did the modeling for us. All right, so what were some of the key variables that increase the probability of fatality when you have a pedestrian vehicle crash on a controlled access facility? One of them we found was truck volume. So with higher truck volume, the higher probability of fatality occurring if you have a pedestrian vehicle crash. We also found a positive correlation with the maneuver type SCL, which we're showing in a small diagram here. So vehicle going straight, pedestrian crossing from the left, perhaps because a driver is less likely to anticipate a pedestrian crossing from the left versus from the right. And also a higher probability of fatality if the pedestrian is male, perhaps reflecting different risk-taking behavior for men compared with women. Okay, the next slide, please. Now, repeating the exercise, but this time looking at fatal or incapacitating injury on non-controlled access facilities. Some more variables turned out as statistically significant here. We found that the probability of K or A severity will increase with the pedestrian's age. Once again, the maneuver type of SCL came up, and also SCR here. So both of the common maneuvers where the vehicle is proceeding straight as opposed to making a turn or parked or backing. This would be intuitive here because going straight, the vehicle is probably going faster than if the driver is slowing to make a turn. We also saw increasing probability of K or A severity with higher visibility, perhaps correlating with speed. Drivers may choose higher speeds when they have better visibility. We also saw increasing fatality or incapacitating injury with increasing outside shoulder width. Now, that's not to suggest that the wider shoulders will increase crash severity. That probably correlates with other conditions or other, especially geometric conditions or maybe just other roadway conditions. So that's always one of our challenges. We have variables that come out as statistically significant, but we also have to ask, okay, does the variable correlate with other conditions that we don't have data for? Interestingly, we saw probability of high severe crash decreasing with sun glare being present. That may seem counterintuitive. Why would you expect sun glare to decrease the crash severity? Well, we weren't the first ones to observe this. We saw it in the literature as well. We were able to corroborate the trends that we saw in the literature. And the explanations we found in the literature were that there's a correlation with speed. If sun glare is not present, drivers may choose higher speeds. And there's also a correlation with time of day and with peak period congestion. So if we're looking at the morning peak period or the evening peak period, we have more pedestrians, but we also have more congestion. So the traffic is not moving as fast. So speeds will be lower, and speed is definitely highly related to pedestrian vehicle crash severity. So what we saw there was a corroboration of trends that we saw in the literature. Next slide, please. Okay, and that's actually it for our technical presentation. We're showing here the various people who helped us with this project, and I believe at this point we can open it up for questions, either for me or for Minh.
Thanks, Mike. Yes, are there any questions? We'd be happy to try to address those. Go ahead. Is it Sohail?
Yes, thank you for your presentation. I'm working TTI in Austin office. So, I mean, your model just show pedestrian crash and use like ML model for binary classification. So, I mean, my question is like, why you think that SVM model is like good? Because in case of like, we have just a lot of ML model for binary, like decision tree, random forest. So yeah, that is my question.
Okay. Why we thought it was good?
Yeah, SVM model is good.
Okay. Well, we were looking at those some of the results from the matrix, the confusion matrix, for example. I think. Right. Oops. Right here. Right. Some of the metrics here, but also some of what we were seeing in terms of the actual versus the predicted. We felt that it resulted in a very good results. So in other words, like for example, in this example here, 50 of them were actually intended based on our training data set, and then the prediction came back as intended as well. And then same thing with the unintended versus unintended, and then the false positives, if you will, were less. Does that answer your question?
Yeah, and did you evaluate any other like precision recall or AU score for this model? How was
Yeah.
this score?
Yes. Let me just ask if our modeler is actually on the call here, and he can get into the details of that if you want. Amir, are you on the call?
Hi. Yes, can you hear me?
Yes. Did you hear the question?
Yes. So in our paper, the details of the precision, recall, and other metrics that we considered is also included. So hopefully that's a good point of comparison with the small sample size that we had, especially in case of text as our input. I believe based on the experience, we can say it's relatively impressive results, but of course there's always room for improvement, and we're looking to better fine tune it and perhaps use newer models that have come out ever since.
Yeah, okay, got it. Thank you. And another question, can I ask another question?
Sure.
Yeah, and you use like ULU B5, which is like real object data detection. I mean, does this project that can be actually like pedestrian one, they're just crashing, that can be real-time data collected and train the model to find out the whatever the pedestrian is crash or not?
I'm sorry, I didn't quite understand.
Oh, no, yeah, my question is like, this project, can you use like ULU B5, which is like ULU B5, which is like real time object data detection, or you have to plan it will be used next?
Okay. Yeah. The reason why we use the YOLO for that part of it, right? And again, we're not looking at these are static diagrams that we're looking at, right? These are not video or anything like that. And so we were using that just to identify really the relative positions. And this is all outlined, this is all described in the report. We were looking at the relative positions of the vehicle as well as the pedestrian so that we can determine at, where they initially started versus where they were at the point of impact. And then comparing those positions, that's how we were able to, again, from that output, feed it into our SVM models to determine the maneuver.
Yeah,
Does
okay,
that
got it.
answer your
Thank you.
question?
And yeah, thank you. And I have a lot of questions I will ask later if I have a chance. Thank you.
Sure. Anyone else?
Yeah, am I audible?
Go ahead.
Yeah, it's Dileepan from India. So I have three questions. So my first question is like, basically during 2020 COVID, there is a lockdown in throughout the world. But how the pedestrian crashes, it will be steady in Texas, because can you go to that slide and show the data? Is there the first slide, I guess?
This one?
Next one, before that.
Oh, this one.
Yeah,
Mhm.
yeah.
Uh-huh.
So regarding that pedestrian crashes, so most of the time it will be like it reduced drastically in other parts, but it is a very slight differences. Can you tell me, like, because we are from India and it reduced a lot, because in Texas, US it is reduced a little. Can you show me some light why it is very less on this?
I'm sorry. What was the end part? Show us what?
Shows like why the pedestrian crashes is very less, even though there is a lockdown in your city or country.
Okay, yeah. So I'm sorry, this graph hasn't been updated. I think there's a more recent data than this. This does show it to 2020, but I think we have it now through 2022. My understanding is that it still has actually increased, not as rapid, not as fast, but there's a slight increase. Part of that, I think, is during the pandemic, and you're right, there was it was shut down for for a number of months. And you can see that's where a lot of the vehicle traffic just dropped off the page, right? But we saw an increase in terms of the fatal crashes. A lot of that was due to speeds. But we saw a lot more people also, I think, using other modes, pedestrians, for example, just as a recreational thing. We have some evidence of that, like, for example, in our metropolitan planning organizations data in terms of their monitoring of trails and whatnot. They did see an uptick, and we actually have some of that data showing that there was an increase in terms of pedestrian activity during that time. But again, that's just that was for some time, and it basically returned to normal. But I think overall we do show an extension of this trend, just not as sharp, if that's what you're asking.
Okay. Yeah, my question is like, this is a pedestrian crash for all US, or it is for the particular Texas?
This one is for US. This one is for Texas.
Okay. Okay, thank you. My second question is like, did you did the correlation between the outer shoulder and the crashes? Can you go to the particular slide? Outer shoulder and the crashes.
Sure. I believe we considered in our modeling, and I don't know if Srinivas is on the phone, on the call or not, but we considered everything that we had available to us in the Rhino database, which is TxDOT's roadway inventory. But we did consider both the inside and the outside shoulder whenever we had that data available.
Yeah, not this one. Can you go next one? Because it mentioned that, but outside shoulder. Yeah,
this one.
Yeah. Yes. So actually, I'm doing research on this particular shoulder width and the crash rate. Okay. So what we understood from our Indian perspective is like, there is a particular threshold limit. After that shoulder width is increased, crash with this crashes are increasing more. That's a threshold limit for the even shoulder, like say 6 feet or 7 feet. So is there, in your particular study, did you find any results kind of the thing, there is any particular threshold after that the crash rate is increasing? That kind of insight, anything you got in the study?
Oh yeah, great question. I don't know that. Mike, I don't think we looked at it in that detail. Do you know, Mike?
No,
Yeah,
we didn't really.
We did not look into that detail. All we were trying to say is if there is a correlation between the variables.
Okay, that's fine.
Great question. Anybody else?
Yeah.
I'm sorry, go ahead.
Yeah, my question is that the correlation between the outer shoulder and the crash rate. That's fine. That's fine. I'll get the answer. If you have anything after some time, you can share the details with me. Also, my
Sure.
third question and request is like, I'm from India, so my most of the team members it's night here. Can I get the video recordings of the session so that I can share to my team?
Mm.
Is it possible?
I believe so. Mike Manser, I believe your team is recording this, right?
Yes, sorry, I was muted. Yes, we're going to have a link to the presentation on our CTS website. So that's cts.tti.tamu.edu. And then Min's report as well. I put that in the chat window. That report is on the CTS website as well.
Okay, so I can
So-
download it from there, right? Is it
Yeah,
open? Open?
Yeah, it's open. Yes,
Okay.
it's a public-facing resource. So, Min, I do have a question and actually a comment that precedes it. So I'm always interested in like how these results apply to our researchers within CTS and across TTI, of course. I know that on the TxDOT side, CTS, we do a tremendous amount of work for TxDOT doing education and outreach activities to help address and improve transportation safety in Texas. And Elizabeth is online. She's the pedestrian program manager over there and has really been serving as a great guiding force for us. TxDOT encourages us to look at high-risk areas, like high-risk communities, and then focus our countermeasures, our ed and outreach materials at those communities, and rightfully so, right? We're trying to hit those areas with material to help improve safety where it's needed most. So my question is, it seems like the results of this work could be used to really kind of narrow down on some of those geographic areas if you needed to. The challenge is the sample size gets smaller and smaller, I realize. So my question really is, how do we balance that out? We have this strong need to identify, where our resources are supposed to go in different communities and how to, what are the factors that we need to consider, like glare. I could see that like, okay, ed and outreach materials could go to people who like a roadway that has a glare issue, and that could start to be seen through your data. But in my head, there seems to be a sample size issue as well. Like we can narrow down to a specific geographic area, but then maybe the results are less stable. I know that's not the correct term, but maybe less valuable with smaller sample size because we've reduced the geography down. Any comments on how we can balance these two interests where, the researchers could use the results in a more focused way in those communities, or can they be used in that way?
Yeah, I'll take a shot at that. And Mike, feel free to jump in if you want, Mike Pratt. But I guess the short answer is it would be great. Ideally, in an ideal world, if we had more data in our data set, obviously, and we were able to apply it to the entire data set. With regards to the weather and the sun glare, we did apply that to all of our data sets, so the 4,400. Keep in mind that, like I thought that was a very interesting find in terms of the sun glare being a possible contributing factor. But keep in mind that this is only for the pedestrian crashes, period. We weren't looking at all all type of crashes. And I think if we looked at all types, I think we would see even higher numbers there. That it could be a contributing factor that sometimes it's just not recorded by the officer, either that the witness or the persons involved either didn't tell them, or the officer for whatever reason didn't record it. So I think that has I think we can do more with that type of information. But you're right, when we drill down to specific locations or corridors, then we may not be as confident, if you will, especially with predictions, because then you're working with a much smaller focused set. So I think it's the best that we have right now, but there's certainly room for improvement, like Amir said before, in terms of what we have, and also really trying to apply some new, even newer techniques. Like for example, we didn't get a chance to explore using ChatGPT at the time because of various reasons, but now that's definitely becoming more of a possibility, and we would love the opportunity to do that so that we can refine our process and hopefully get more accurate results, and then we would have more confidence in using it and applying it really to like to screen a lot of the things that I was kind of alluding to in terms of the definition of the pedestrians for our purposes in terms of the intentionality. We think that could be used for a good way to screen out the ones that, like for example, the ones that are unintended. And if the majority of those are people that are getting out of their car and getting hit, well, then that's a educational campaign that you can use to address perhaps those segments of the population that are at higher risk.
Yeah, absolutely. Okay, I see thank you very much, Minh. Thank you very much, Mike. I see we're coming up right at the top of the hour here. I do just have one or two short comments. I want to thank everybody for attending virtually. This presentation series is intended to, again, share the results of some of the CTS projects that we do with stakeholders within TTI and then outside of TTI. So I very much appreciate your attendance today. The next presentation in this series will be held in June, and we're going to be very shortly identifying the date for that. The time will be about the same, kind of over lunch hour, but we're working through the date right now. We will have that identified shortly, and then we will post that on the CTS website. And again, and I'll ask Laura in the back of the room here to put our CTS website web address in the chat window. You can visit that, or you can email me. Laura will put my email in that chat window as well. If you have any questions about today's presentation, I do encourage you to connect directly with Minh or Mike. Their email addresses are on the TTI website. So if you just go to tti.tamu.edu, there's a people button in there. You can select that and do a search by their names and come up. And do please get a hold of them if you have any questions about today. With that, I want to thank everybody for joining us today. Very much appreciate your participation, and we'll talk with you in June. Thank you.
Thank you, Mike. Appreciate it. Thank you, everyone.